live. Seems all right, I think. Let me check. All right. Now, today, we're gonna what we are gonna talk about. Actually, we're gonna study algorithms, but I haven't changed the title of my stream, so maybe I should do it. I should do that first. I am studying leetcode. Let's do it together. Do it together. I have some questions that I need to review. Let me open my notes here. I have 7 days plan that I created before. We can study with invert binary tree. It's a good question for uh, you know practicing recursion. So let's see how well I remember that question. So it is one of the easy question listed on leetcode at least, but I think it is not easy because if you don't grasp the idea of recursion, then it becomes quite hard. So what it asks basically, imagine we have a tree and we need to basically invert it, like imagine there is a mirror here, and this left part will go to right and right part will go to the left part, and it applies to the child as well. So let's see if we have, no, we don't have. So for this question, let's see, 1 2 3 4 5 6 7. So the end result will be, the root will be same, and then 3 will be here, and then 7 will be here, 6. So realize that we change the position of childs as well. So 5 will be here and 4 will be there. So this is the inverted version. Let me click there. All right. So this question is among one of the easy questions because the process that we apply for the root, we can apply it for their, like, for its children as well without a change. I guess that is why. So for me, the recursive questions contains one or two different cases. First one is like a, well, what I call is like a real process, real job, because in this question the real job is like changing the left child and right child, all right, the swapping. That the swap operation here is the process, and the second one is applying this recursively. So the process is like if we are root, all right, and we need to make the left child with its right, and we need to make its right child its left, but since we lost it, it is a good idea that we first hold its left child's reference somewhere so that we can use it here. So this is the core project, and then the recursive part comes. I imagine the recursive part like this, all right? Let me copy this part. Scroll down a little bit, paste it, and think about it. The thing is that, like, imagine like left sub 3, something like that. Like, we are not process like or apply the recursion like how the CPU does, because we are not a computer, we are human beings, so we need to handle this like let's say mathematically, all right, instead of going uh, each stack frame. We are not compute each stack frame. So we have here the left subtree, the left, and then here we have the right subtree. So in somewhere in our code, we are gonna make this call, right? As I say, func left, like this is obviously root dot left, all right? And then somewhere in our code, we need to do like we need to make these calls, all right? There is no escape from that. So we have this. I imagine what will happen after I call these methods. Since the structure is like a binary tree, like the structure is same for each node, all right? Each node can have like a 1 or 2 child, so the structure is same. So we can apply the same logic for each child. So I imagine what will happen after after these methods return their value. So from the perspective of this root, when we call func left, actually let me write it using a different color. Yellow will be better. Func left, all right. So of course, after we call this, it will be the root, and then it will make another like a left call here, but we don't process it like this because we are not the CPU. So, but instead, we imagine what will happen after it returns. So we call it, and after upon the return value comes to root, that where this function is called, when it returns, we will have like a inverted binary tree, inverted version of this tree, all right? Actually, since I use the mirrored form, we can, let's say, apply the invert again. So the version will be here. Let me do it like this: 3, 6, and 7. So when this function return to root, the structure is like this, all right? And then we're gonna call the func right. But we are basically time traveling, all right? Like the recursion concept is about the time traveling. Func right. So again, we're not thinking about like the stack frame wise, but instead time wise, all right? So when this function, like this function is called, and after it returns, the structure will be like here, 2 here, and then 4 here, and as right child we have 5. So the structure will be like this after both of these functions return their value. So now I can think now it is time to think about what should the root do, all right? um, is there a sound in the background? All right, because now we completed our job for left sub 3, all right, and right side 3, so we feel amazing. So now from the first perspective of root, we need to change obviously these nodes, all right? So as I called it before, like we have process like the real job, like a swapping operation, and then the positioning or imagining, or let's say positioning the recursion correctly. All right. We talk about recursive part. So we handled the left subtree, we handled the right subtree. They are done. We completed what we should do with them, and then we now think about the root. So for root, as I write before here, actually I can copy and paste it over here. I think yes. So this is the process part, because we apply the very same process in these subtrees too. So if you think this like a stack frame wise, you'll see we're gonna be applying this process for each of the nodes. Let me drink my water. Let me check my CPU. Seems alright, I think. Hold on a sec. Alright. So this is it basically. So you may ask that what would happen if we use this process like above the function calling, because there can be some differences based on the position, based on the position of process. Let's imagine, actually let's talk about it. Let's say we call these recursive functions before the process. So let's say we have a tree, all right, and we have its subtree, all right, and then right subtree, all right. So if we make first recursive calls, like when this returns, the left subtree is inverted, and we call right. So when it returns, it is inverted fully. So after that, we apply our process. This is the logic we applied. And the second one, we can, again, we have left subtree and right subtree, but here let's say we swap, all right. So the tree we have, let's say we first swap. So tree we have would be, let's call it 1 or 2 and 3 here. So if we apply the process first, then we have 3 here and 2 here, but their subtree, all right, is not inverted. So we need to invert them too. So I guess there will be no difference, but there are some questions that the order may affect the time complexity, like a big O notation. So for this question, the time complexity would be, I guess, depth of 3, I don't know. And depth of 3 is like a log n, maybe. Let's ask this actually to AI, because I'm not quite familiar with the time complexities. For most of the 3 questions, it depends on the height. So not the number of nodes, but the height. Actually, let's think about it, all right? So we make 2 function calls, and how many times we're gonna make these calls? We can maybe think about this. How many times? Let's say the first time, the second time, and then there is no child. So the time we call 2 times, and here 1 right call. And here we have 1 right call and 1 left call. So we need to generalize, we need to formalize the number of times that we call these functions so that we can have an idea of about the time complexity. Maybe it is a good time to ask it to let's create another session. Actually, maybe I can open my another project that is, yes, I use for learning algorithms and other stuff. And also we can create some animations too, because animations help visualize. So maybe we can ask, actually first position them better. um all right, so let's ask. So now I'm studying invert binary tree problem. I wonder how am I supposed to know the time complexity of this, because in each stack frame we make two calls. First one is for left subtree, left node, left child, and the second one is for right child. But um, like, should I know? Like, should I calculate how many times we make call, or what is the way of doing that? Because as far as I know, for the tree problems, most of the time it's about the height or depth of the tree. So I guess here in our case it is log n, right? So can you guide me a little bit? So here I have a skill in Cloud Code. It behaves like a teacher or tutor. Instead of dumping the code, it explains and it guides me. Let me click here. All right. And let's see what it says. Good, you came with the hypothesis log n. That's exactly senior mode. Predict before asking. Let me grade your question at the end. First, let me push back with one leading question. Exactly, what I need is leading question. You said for 3 problem, it's usually about the height depth. This instinct is half right. Oh yeah, I know. But it is mixing up two different costs. Height depth tells you one of them, not the other. All right, all right, all right. When invert tree runs, when inventory runs to completion, how many nodes does the function body actually execute on? Trace it. Root calls left and right. Each of those calls left and right again. Does every node in the tree get touched, or only the nodes along one route to left path? Tell me your count first. Actually, since each of the nodes call left and right, we make two recursive calls. So I guess we make two recursive calls for each of the nodes in the tree, instead of, like, let's say root to leaf. I mean, each node should have two recursive calls. So maybe not log n, but 2 times log n. Is that what you mean? I guess we are not answering it correctly, but let's see. Not quite. Yes, this is expected. And I can see the snack. You are still multiplying onto log n. Actually, the time complexity, like, it doesn't matter, like, the multiplication with constant numbers. So there is no difference between log n and 2 times log n in terms of the time complexity. So, but let's test with an actual count instead of a formula. All right, take a small perfect tree. Those each call 2 more, etc. Count it concretely. How many times does the function body execute in total before it is all done? How many times does the function body execute? I didn't understand this part. Before it's all done, I think it means before it returns. Just count the calls that actually run on a real node. Ignore the null children for now. Give me the number of this 7 node tree. Actually, I don't understand. I don't understand. So, like this node, we'll call this one and this one. So, as the AI suggested here, I guess it is 7 calls, but now 2 calls 4 and 5. All right. 3 calls. Actually, it is number of nodes because somehow I thought that, like, imagine here there were some other, nodes, all right? Just imagine it. But even in that case, it doesn't matter because you make one function call here, and then it can call these parts. But every one of them is like a one function call. So the remaining part is like a unwinding returning phase. So while returning, we don't consume that much of our CPU time. So again here, like we have 6 nodes here, so plus 6 calls, 6 more calls. So I guess let's press on tab. 7 calls. 7 calls, 1 per node. Yes, for each node we make 1, right? All right. Yes, 7 nodes, 7 calls. All right. So the time complexity is O(n), not log n. All right, because for each node we need to make one call for that. All right. I guess the log n part is for a different question. Every node gets visited exactly once. Yes. Now the part you were half sensing, where does log n actually live in this problem? I don't know. Space complexity. It's not nothing your instinct was pointing at something here. Think about the call stack at its deepest moment when invert 3.4 is running. So invert 3.4 running. So yeah, we are in the deepest point. Which calls are still sitting open on all right, so like when this is running, like let's say the function call like is 4 here and we are in his stack frame, all right, the root is 4, so we should, like, we have two stack frame above, let's say above us, I don't know, maybe below us, let's call above us. So like this is the node 2's stack frame, and in this stack frame we have, let's say, func4, all right. So and from the perspective of 2, we are in the stack frame of node 1. So this is the stack frame of 1, and here we make call for left child, all right. As we call it, we open another stack frame, and here for func4 we call, like, we create another stack frame. So we have three stack frames. But how about the right child? Actually, for right child we haven't called it any of them. So even we call a right child, that would be from the func2. So after this return, like this function, let's say stack frame returns, all right, then we call we create, let's say, another stack frame. So the number of stack frame doesn't change. There's a limit to that, all right. So we call func5, which is right child of it. So we are here inside the func5 stack frame. So what do we have here? What we have here is that the maximum amount of the stack frame that we can have is 3 here. And yeah, so how should we formalize it? List them and tell me how many frames are stacked. So let's, for func4 we have func2 and func1 below us in the stack. Yes, in the stack we have func1, we have func2, and then func4. This is our stack. So we had 7 nodes, and we can have we can have 3 in our stack at most at a time. So how should we formulate this? All right, let's see. Let me close a few tabs in my Chrome. All right. All right. Exactly. Max 3 frames for 7 nodes. Yes. The stack depth equals the height of the tree. All right. Now formulate the relationship. You had 7 nodes and depth 3. Notice. All right. So since we are in world of, let's say, power of 2, because let's say we have 1, which is 2 to the power 0, I think, and then here we have 2 nodes, 2 to the power 1, and here we have 4 nodes, 2 to the power of 2. So, and here, you guessed it right, we have like a 7, not 7, 8 to the power 3, and then 16. So, all right, so let's continue. So we know this, but the formalization step: max 3 frames for 7 nodes. Now formulate the relationship. You had 7 nodes, step 3. So are we gonna say that, what is the, we need to find the 3 using what? I guess the depth. So is depth 2 or 3? This is the first step, this is the second step, or first level, second level, and the third level. By third, we already use 3 minus 1, obviously. Or forget about this a power part, but instead we have, let's say, first level, second level, and the third level. And since we we can go up to third level, this is the maximum amount of stack frames that we can have in our stack. So it is the depth. So the formalization is this, basically. Because as soon as I saw this part, I thought maybe we should have a formula. I should have a formula using this part. But so what is the 3 in terms of 7? Depth equals log 2 7. Log 2 7. So log 2 8 is log 2 to 3. Since the base and the this part is equal, let's say we can remove that part and we have 3. All right, so it says that it is almost same with log 2 and 7, and again 3. Like this part, all right, is same as this part, but when we use logarithm, it gives us the depth, and the maximum number of stack is equals to depth. So since our formula is all log n, this is the space complexity. All right, now let's continue. Actually, I have studied these questions, so maybe it should be better if I start from the from the back, or continue from where I left off. Lowest common ancestor, longest common subsequence, cadence algorithm. All right, I created even an animation for that, loop detection, heap sort. I guess we can start with heap sort because I have animation, like I should have animations over here. It is not in greedy, but sorting, yes. We can study actually here, like here in this video, about sort algorithms, because these is there a sound in the background or not? Because there's a threshold point when I do it a little bit lower at that point, there is no sound at all. I guess you can hear the sound. So we can continue with the sort algorithms because this is what I want to study. Because these sorting algorithms are asked during the interviews, we should be like, is the stream is fine? All right. I don't know. I think anyway. So these questions are important, all right. We need to know their time complexity and space complexity very well. But is there a problem on my recipe? Let me refresh the page. All right. Now it is better. So bubble sort. The renders. We have the second version. Can we study here? Actually, let me do this like this. So the bubble sort. Like here in bubble sort, we have we have pairs, all right? Like we have a part length of 2, and we move that part until the end of the array, and for each pair the atomic step we apply is just swapping if the left part is bigger than the right one, all right? And when we reach end of the array, we start from the beginning again, right? Let's see the animation. So like we are here, and like we have 3 and 7, so they are in correct position. We have 7 and 11, they are in correct position. And then we have 11 and 1, so 1 is right side of 11, so we need to change, like we need to swap them. All right, and we are swapping them. And then 4 and 11 should be in correct position. No, we have 11 and 4, 4 is on the right, so we swap and recognize or realize that we we make the two part move right. All right, and then again 11 and 9, 9 like is on the left, on the right side, so it should be left because it is smaller than 11, so we are swapping them. Actually, maybe I should open this in let's open this with this one and open with QuickTime. All right, this is, I think this should be better. All right, and 2 and 11, yes, we are swapping them. Again 6 and 11, we are swapping them, yes. So at the end, again, the 8 is not in correct position, so we swap. So at this point we should start from the beginning, right? But also realize that the length of the some sort of, like we're gonna use for loop, so the end position or the limit of that for loop we decrease. All right, and we start from the beginning again. So we have pair, we move these two length of two part, we start from the beginning and we move it again, just like we done this before. So basically we are swapping if the smaller value is on the right. All right, and let's see what would happen after these steps. So like, is this platform gonna forward this or not? But most probably not, because we decrease the endpoint. Let's see. Actually, yes, no, we didn't go there. So upon we reach the end, we decrease our next iteration's size. All right, at least in the animation we see this. So, and now we should start over. So again, we have 3 and 1, and 1 is smaller. We swap them. Again, we hit smaller, we swap them. All right, so as we hit the limit, we're gonna decrease the iteration time and then start over. All right, so this is the animation. I guess I understood it. So now it is time to type its code actually. So, and actually the thing we should know is like its time complexity, but it is good for practicing too. So we had these bars here and we were swapping them when we find the smaller one. So and we had a concept of length of two platform. So basically we're gonna have some sort of for loop, obviously, and we should have let's call it length. So like we should, or actually like this is visualization. like a length of 2, like a platform of length of 2. But in the code, maybe we don't need them at all. Like we don't need it at all, because the the thing is like the thing we are doing is like uh, starting from certain point and then it's next. So instead of some platform of like 2, maybe we should do something like let's say we have our iteration variable here I, so maybe we can have I plus 1, all right, so that each time we just compare. So, and let's say we have an array of R, let's say ARR. So let's have a if condition. If the I plus 1, if the I plus 1, let's imagine this point. If the I plus 1 is smaller, like I mean the value at I plus 1 is smaller than the Ri, yeah, so we should do some swapping operation. Let's call it swap. I don't know how we can do it right now, but let's call it swap. Or even better, with a like instead of using a command, let's call it swap function. For swapping, we need again we need the indices, right? Let's swap this with this, I guess, and also we should give the reference of the array. All right, this seems okay to me. So so now we like this is the core part. All right, all right, this is the core part. So we realize that we don't need to have a platform like some sort of base platform, like bar or something, length of 2. But instead, like the logic is like comparing the value with the next value. So I realized that we can make use of the iteration value variable here I. So this is the core part. Now we need to think about, like in the animation, as we reach, let's say, to the end, all right, as we reach to the end, let's say we swap 2. Like, is the sound is high or not? I mean, let me. All right, I think it is better. So as we hit the, like, we need to define the hitting to end clearly, because let's say this is I and this is I plus 1. All right, so this means we hit to the end. All right, so the let's say the most, like the highest value that the I can get or should get is what? Not the length, but length minus 1, I think, right? Because let's say we have length of 7 and 5 is the highest value it should have. So 7 minus 1 is 6, and smaller than 6 is 5. All right, this is all right. So this is the how far our I value can go. But also now it is time to think, starting over. So like this is the first, let's say, first iteration, right? But we should do this again, and we should we should be able to change this part dynamically. So this part should be dynamic. So maybe in this, instead of using length minus 1 statically, we should have a variable. We should have a variable. So let's call it and. And we should have a for loop or something to, to make this part run again. So maybe let's let's copy and create the smaller version of it. All right, let's copy and paste it. Can I? No. All right. Let's remove the yellow part. All right, take the green, and now like a let's imagine we have another for loop on top of this for loop, and this for loop should give the end value to here, right? I mean, it should. I know. So no, like maybe while loop. Maybe we can use while loop too. Like let's say we have a variable called end, and like after the for loop, like this for loop finished, the end value should be like this, right? One smaller than the previous iteration. We can have something like this. So how many times this for loop, like the outer for loop, should run? Can we open the? Oh my god. So how many times the outer for loop should run? How many times? So how many times? Like imagine that this platform, all right, and let's start this again. Imagine this platform, and it is going to the end and then start over. All right, so we handled the dynamic part here. So we changed the endpoint dynamically. But the outer loop, like I'm thinking right now about how many times the outer for loop should run this inner for loop. How many times? How many times? And I think it should be about the length of like our input, length of our input. So we go to the end, we start from over, start from beginning, um, and then again. Is that a base case or something, or it is about like it is only about the length? Pass 4, pass 5. Hmm. Hmm. I guess here, since they are ordered, maybe we also have some sort of logic that I don't know. Like I didn't understand this part of animation actually. Pass 5. I guess there is something wrong with the animation, but I guess like I understand why this happens because the remaining part is already sorted. So maybe we can have um, a logic for that as well. Maybe move it there. I don't know. So I don't know. What do you say, guys? Let's make it bigger. How many times should the outer loop iterate? Like for loop seems good to me. All right. Let's check the stream. All right, seems good. Dut, 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 dut. We have let's think about it, all right? Because I don't have any idea. Maybe we can get a quick, guide from our AI. But I just wanna come up with an idea at least, like because we we found the endpoint, like this is dynamic. It's like we now should find the how many times. Let's assume let's say J, all right. I know I'm using the convention wrongly, like this should be I and the outer should be I, but let's go with it. Let's say the J, like how many times J smaller than, let's call length, all right. Let's call length. So what would happen in this case? um like this is inner loop, all right. This is in inner loop that does the swapping operation. Like this is inner loop. So the outer loop is when we start from over, like this is the outer loop. So um it was the first pass and then the second pass, and we start from over again. We start over again. Hmm. It shouldn't be this hard, but let's ask to AI, all right? There is no time to, uh, lose. Let's create a class station and ask. So we are studying bubble sort algorithm. So we understood the inner loop. Like we have an inner loop, and it starts from zero and until the I smaller than length minus 1, and inside of it we have a if condition. If the value at I plus 1 is smaller than the value on r I, we swap, like we call the swap function, all right. I comma I plus 1 comma r. So we share the reference of our array, and then I and I minus 1. Or even uh, we don't even maybe we don't need to like make it two variables. That's all right. That's all. Let's just assume it takes three variables. All right. After solving our problem fully, we can enhance it, optimize it. So now, like, we are thinking that for our inner loop, like inner for loop, like I said that length minus 1, but we should have a dynamic value like a maybe and, like a e and d, all right. So because in bubble sort, in each iteration, in each iteration, the endpoint we go, I mean the iteration of outer loop or inner loop, I don't know how to define it, but in each pass the endpoint is getting smaller by 1, decreasing, decreased by 1, all right. So this is why we thought that we need a dynamic value, so I call it and. So now we are at the phase of having an outer for loop or while loop, I don't know, and this for loop should make us start from over. So it reminds me, like, actually starting from zero is the inner for loop's I value, like, or start value. Actually, like this is that's something that makes us start from over, because each time we call, we trigger this for loop, it starts from zero and goes up until the end, let's say length minus 1. And we now, since we now have end variable, it should only go to, like, the end value is changing too. So the remaining part is like a how we can trigger this for loop. And after this for loop, actually I imagined, like, after the end after the inner for loop, we have like a and equals like a minus equals 1. So we are decreasing the end. All right, we are decreasing the variable end by 1 after the completion of inner loop. So the remaining part is outer for loop or while loop. I don't know. What do you suggest? Guide me. Let's paste it because sometimes if I talk that much, so it can stuck. Let's wait it. Let's wait for it transcribing. Currently warming up. Oh my god. Let's find what we said. History. All right, this seems all right. Copy the value, paste it. Like this dictation is helpful. Actually, no, like and activate tutor, like a not tutor mode, but tutor mode 2. I guess it will understand us. So yes, tutor mode 2. So like how many times? Like I need to know, like we need to know how many times should this for loop run. How many times? Like only thing I need to know, like first thing I need to know, like we need to know is how many times. Is there someone can like tell us how many times? Because let's call it like 1 2 3 4 5 6 7 8 9 10 10. Let's call it 10. All right, 10 times. If we start 10 times, what would happen? I don't know. Good thinking. You got the inner for loop and the shrinking end nailed. Yes. You ask for or while. What do you suggest? But you already have a hypothesis hiding in your own words. So before I answer, what do you lean toward and why? Actually, I lean toward while loop because I don't need a start index. I just need how many times? Like a iteration, like a number of iteration I need. I mean, and one little question to point: the outer loop's whole job is to keep firing passes and shrink and each time. So ask yourself, what value does and start at, and what value does like this is a good question. This is a good hint. So I guess most probably we're gonna use a while loop. All right. So let's remove this part. So because the question it asked is wonderful, like a sometimes even the asking correct questions leads you in correct direction. So let's say we have a while loop here, and the question or the hint it gave us, the AI gave us, is the start point of end. All right, maybe we can have end variable here, and end can start at length. We calculated this length minus 1, and it should stop at 1 because or 0 or 1, I don't know. If you can name those numbers, the choice between for and while almost makes it stuff. Take a shot. So, like end variables should start at length minus 1 because we compare like a I with I like I plus 1, so that our index I cannot be um, last index, because otherwise we would have I minus 1 and we would have out of bounds exception. We may get out of bounds exception. So since it should smaller than, you know, length minus 1, so this is our end. And your for second question, what value does end stop at? What value does end stop at? It can be 1 or 0. I cannot see it clearly right now because I don't know. So actually no, like I don't see it. Like yeah, maybe 1 or maybe 0. So what is the difference? Like the difference between the times, like how many times we trigger our inner loop. So it is quite important. So let's call it 0 because at 0 we should run one more time and then we, you know, stop. Or like what you asked? You said that the outer loop's whole job is to keep firing passes and shrink and each time. Actually now, like I answered, you know, those questions. You should first verify my logic for the, you know, when the end stop at, what value end stops at, and then you should guide me how many times like the outer loop should trigger. All right, let's see. And then we can also, you know, maybe change the thing we have. Let me write bubble sort. We are studying bubble sort. Yes. Your end start is correct. Yes. Your reasoning is exactly right. And like minus 1, all right. So that I minus 1 never runs off the array. Yes, runs off the array. Now the stop value. Don't guess, trace it. That's the senior move. Pick the smallest input that reveals the answer. Pick the smallest input. Take, so let's say our input is like a 3 to 1, length of 3. So and starts at 2, like 0, 1, 2. Like, does it? We make smaller, smaller than n, so yes. Inner loop runs, I 0 and 1, walk it. Where does the 3 end up? All right, so what it says is that imagine we have 2, 3, 1, and we have our for loop over here, and then it is smaller than the length minus 1. Length is 3, length minus 1 is 2, smaller than 2, and starts at 0. So we have this function, we have this for loop, right? We started at 0. All right, so we get this part, we swap them. All right, can I move it? So and we go this part, and we're gonna have like a 3, 1, and again we do swapping, and then that's all. So 2 times, like inner loop, 2 times. So what about the outer loop? So this is the first iteration. So like, what do you mean, man? Pass 1, all right. The inner loop runs I1, I0, and 1. All right. Yes, we have seen this. All right, that's fine. Walk it. where does end up? So it ends up at, you know, here, because we swap. All right, we swap like a in first iteration of for loop, it becomes like a 2 3, and then in the second one, like in the second iteration, it becomes, you know, 1 and 3. So like this is the end, like end position, final position, final version. Pass to inner for loop runs 0 only. Now we are in the second. All right. Now let's think. So the end, like we decrease the end by 1, right? So actually, like maybe I type it wrongly here. So like end was 2. Yes, like end was 2, and then in the second, like in the second outer loop iteration, it is 1. All right, it is now 1. So we're gonna run only once. We start from, you know, we have like a, let's use another color over here, 2, like a yellow or white. Let's call it white. Let's use white. 2, 1, and 3, and we only, you know, run once, and again we swap these. Wonderful. We swap these, so we end up with 1 2 3. And so now it is time for us to know what we should do. So like we run the first like a for loop twice, and then once. All right, now our mission is completed basically, but like a outer for loop, like a end was 2 here. Oh, all right. Now we should think about the end. End was 2 over here, right? Yes. So end was 1 over here. Yes. So and we completed our job. So we don't have any iteration when the end is 0, right? Because if it has, I don't know, man. I don't see it. To be honest, I don't see it. Let's see. Pass 3. If it run, yes, if it run and 0, how many times does the inner loop body execute? So it says that if, let's say, if the end is 0, and we once more inside, like we once more trigger the for loop, like this for loop. I mean, we triggered this for loop, and the end is 0, so it wouldn't run it at all. So I guess we don't have an issue at all, right? So I tracked the, you know, iteration loop, and even when the end is 0, since our inner for loops, you know, end position is, let's say, smaller than end, right? So the inner loop won't start at all, so we don't have an issue. So back to my question. What was my question? So I guess it shouldn't be a problem, right? So I guess we were thinking about the like a value of end, like how should we determine this? It can be 0 or 1. We don't have an issue because our inner for loops, like inner for loop handles this, you know, well. But can you guide me a little bit more? So let's see how it will guide us. So like we almost completed the bubble sort. All right, after understanding this part, I'm gonna ask it to, teach us the, finding its time complexity and the space complexity, and then we're done, and then we can continue with heap sort. All right, which is more which is more interesting. Like each of these sorting algorithms are quite interesting. Is quite interesting. Let me tell you that. But the heap sort is kind of harder. So exactly right, and that's a sharp observation. The inner loop, or like inner loop's own condition, guards, exactly like this is the term, guards the empty pass for free. So and equals 0 just means run a pass that does nothing. Exactly, yes. That means both 0 and 1 give a correct sort. Yes, yes. The only difference is one wasted, no operation pass. Yes, all right. So correctness versus efficiency. You found that yourself. Good. Thank you very much. So pick the one that does no wasted work. All right. So since we are an engineer, like we are engineers, so stop before the pass that can't do anything. So that means the outer loop should keep going while and is still positive. Now write it. Yes, like and is positive. All right, all right, all right. So now it guided us to decide whether we should have a while loop or for loop for our outer loop. The answer is for loop. So inner for loop and outer, I mean, did I say wrongly? So the outer loop is while loop and inner is for loop. And the inner for loop, like the endpoint is calculated dynamically because, each time the endpoint, like the final position it gets is like a decreasing after each pass, all right? Like, like it is decreasing, all right? So we should have something dynamic. So let's call, we have like a j, all right? Let's call it now correctly j. It starts from over, like it starts from 0, because in each pass it starts from over, all right? After it completes its job, it starts from over. Let's see it, all right? All right, so and we need outer. Oh, not a big fan of the while loop. Using for loop keeps it cleaner by having all the info needed in the loop expression. Exactly, I agree with you. Actually, kind of agree with you because it is kind of opposite for me. Like the role of while loop here is just triggering this for loop. So like uh, because it doesn't, like we don't need the start point. Let's say I starts from 0, or the actually, like the only difference is having the start position. But the from outer perspective, the goal of while loop is just triggering, nothing more than, but more than that. But for loop, for like a inner for loop is like needs the start position in each time, like because as we can see here, like let's start from over, like we start from like a 0, all right, and we go up to the this part, like a length -1, I guess, or -2, like a this index, and the next pass we should go up until the this one. So and the start and end position, we need both of them, but the while loop is only triggers. So like the thing we need is like maybe holding or knowing only the end position, nothing more than that. But for most, for the other cases, having the start and end, of course, can be safer option because you are in control, all right? But in our case, it seems a little bit different. But in the broader perspective, like in the other questions, like having more control over these variables is safer option. So in that sense, I agree with you. So we, j starts from 0 and end is calculated dynamically here. And for while loop, the end should bigger than 0, and we should initialize and here, like maybe length uh, -1 or -2. I don't know. I genuinely. And also after the inner for loop, we should decrease end by 1, so that in each pass it should go one less. All right, it should, like, it goes one less. So like, all right, so now the remaining part is like knowing if this is length -1 or length -2, but maybe we can leave it for later. What I want to know is that how to calculate its time complexity. So thank you for that. I almost fully understand, like, maybe the part where, like, the initialization point for end, if it's length -1 or length -2. Anyway, maybe you can quickly describe it. But the part I want to focus is now is like, how could we calculate the time complexity and the space complexity of this algorithm? Because as I know, like, almost for all these sorting algorithms, time complexity is like a n square, right? Why? Because, like, all of these sorting algorithms is just a little, like, a small optimization, maybe small optimization found on a small part. Because overall, since we have an array, and we need, like, since we need to compare its values, all right, so we, like, as a base case, we have for loops, like a inner, like a nested for loops. So this is the base part or of all of our sorting algorithms. But there are some people who are quite smart, and they find some little optimizations. So here we have a while loop, while outer loop, and like, why, like, you should guide me, all right? Because I can say that when we calculate, when we compare all of the pairs, we got n square time complexity. So how well the bubble sort is better, than the normal comparing? So can you guide me a little bit more? So while it answers that, it is answering that, maybe we can think about the end part, the start position of end, because this shouldn't be that hard, right? So end is the point we go up until where we go, like, this is the end. So we decrease it by 1, but the initial point is, like, it should be so, like, the inner loop j is already 1 smaller than end, all right? Most probably it is -1, all right? So let's say you have 3 to 1 as an array, and you will compare these two and then these two. This is the first pass, and the second pass is only this part. So j value is, like, a j value is here 0, and here 0 and 1. So the initial value it has here is 1, which is like length minus 1. All right. Yes, all right. This is length minus 1, so the answer is length minus 1. Um, all right, because length is 3, minus 1 is 2, and smaller than is 0 and 1. All right, so uh, like we already calculated this in the beginning, in the very beginning of our video, like in the solution for bubble sort. So the ant should get minus 1 as an initial value. Quick answer: on length 1, the inner loop compares Ri with Ri plus 1, and the very last pair you ever need to touch is length minus 2 and length minus 1. All right, all right, all right. Let's assume that we like I understand this part. All right, all right. So now the complexity part. You are circling the exact right inside. Let's count comparisons. Don't hand wave. What does this mean? So um, your ant shrinks every pass. Yes, yes, we do this. Pass 1. Inner loop runs how many comparisons? Maybe I need to take a break before trying to understand this part. So what do you say, guys? So my goal is like now is understanding its time complexity, all right? And after that, we can go with continue with heap sort, and then merge sort, and then quick sort, and then selection sort. For all of them, we have their animations, all right? Because animation is like helps a lot. Without it, I don't imagine myself understanding them at all right? Because I see them impossible to understand without seeing. Because I assume, like most probably, the author of these algorithms, you know, drew their algorithm on this, table or something, board or something, and saw like how they behave. All right, because the core logic is understanding that part, not coding part. Coding part, like we are already using high level language. We are not typing assembly code. So high level language is kind of simple. All right, not quite simple, but I mean, um, if you got the logic part correct in your mind, it becomes easier. So that's why I value seeing the algorithm more than the coding, because as you see, like we have written, we have coded the code part. uh yes, now that you figured out most of it, why I like using for loop for both of them is that I can use its index calculation without giving extra variable. Now that you figured out most of it, yes, why I like using for loop for both them is what is that I can use this index to calculate and without keeping extra variable. All right, all right. So I see. So you are saying that since I have we have like another variable outside the while loop, because in most of the case, most of the case where we use while loop, we have 2 or 3, maybe even more variables that are that are changing. All right, I understand that you initialize the variables inside your for loop, so you don't search for them. I totally get you. I thought now, like, this is another case that I like. I totally agree with you, because maybe we have only end here in this case, but we can have maybe start, maybe some uh, let's call height or something. I'm just saying. So for all of these variables, we should update them inside the while loop. But you are saying that for loop you can handle you are handling this inside here. So that can seem, you know, compact. Let's call outer loops index I. Yes. Then inner loops termination condition becomes length minus I minus 1. Let's try it. Let me understand. So you are saying that we have, like, let's have an index I. Let's call it, all right. So we have a while loop here, like outer, or you are saying that then I can write for loop. Let's call it for loop, the outer, and then we have our for loop inner loop, and we have and here. Let's call it I and J. You are saying that then inner loops termination condition. So termination condition here and is length minus I. Length, all right, minus I minus 1. Let me think a little bit about it. Give me some time to process. So you are saying that if it's zero, it is length minus 1. Yes. So when it becomes 1, yes, all right, because if you make it, you know, length minus 1 in the beginning, so for the next conditions or for the, you know, next part, next iterations, that will also sufficient. So all right. So thank you. Now we solved it using 2 different ways. So there is a sound coming out of my window, but you are definitely right. So maybe remove that part too, and yes. All right. This seems legit. Actually, using even for loop can be better because you see nested for loops in many cases. All right, like nested for loops are used commonly. So yeah. So but for this part, like it starts from 0, but where does it go? Like obviously we are increasing its value, and what is the end condition here? Because in the for loop above we have, like, we start from the upper limit and we decrease by 1 up until the, you know, hitting 0. But here we start from 0 to where? Can you tell me that too? And let me close my window. Can you tell me that too? So we start at 0. Yes, the formulation becomes, you know, length minus I minus 1. Yes, but the endpoint I'm thinking right now. And let's increase this a little bit. Is there a sound in the background or not? By the way, can you tell me if the background sound is good or bad? Inverse. Now we go from 0 to upper limit. Yes. Length minus 1. Length minus 1. This seems quite legit. Actually, yes, inverse. All right. So in while loop, we start we start length minus 1. Yes. And go to the, you know, 0. Actually 0, but in this case we're not going to, you know, 0, but instead bigger than 0. So we pass the no op value, like we don't run for no op time, like a no op case. But what happens in your case? Do we iterate one more that unnecessary move? What do you say about this? Because in while loop, it is bigger than 0. But here in our for loop, we start from 0, and it, as you say, actually it is smaller than length minus 1. Oh my gosh. Let's put it that way so that it looks better. And increase the I. Inverse. Now we go from the upper limit, length minus 1. Yes. Yes, but yeah. From 0. I'm thinking that what would happen if, when actually it is quite basic, like it is the inverse. So if I understand the while loop, version, it is only about the times, how many times we trigger. So here in this case, we are triggering, and sound is good, very good balance between volumes. All right, thank you. So, like, do we have a formulation for how many times we we are iterating? Like, let's find the formula. All right. So let's call it like if we start from 0, and if it's smaller than 3, we have 3 times. So the how many times is exactly what is written here. So if we write here like a length minus 1, we trigger, like we will trigger this inner loop length minus 1 times. So this is the amount of triggering we do for inner loop. All right, so let's see what actually we can continue with heap sort. What do you say, T Carcus? Should we continue with heap sort? Because it will be better if I see different questions. What do you say? We completed bubbles. Actually, we didn't complete the time complexity. Time complexity is the most important thing in this question. Actually, let me refresh the page, because in the interviews, like, the important part is knowing the time complexity. They most probably don't ask you about the implementation of this bubble sort. But it is a good practice to know these implementation, because like it is about for loops and while loops and handling the start and end point. So what do you say, Carcus? Should we continue with heap sort? Because I wanna complete all of the sorting algorithms. I wanna understand. In general, yes, you are mostly done with bubble sort. There is time complexity. Yes. So maybe we should complete it, and then we go for the heap sort. So quick answer. Yes. So your end shrinks every time. Yes. So pass 1, inner loop runs how many comparisons? So the amount for our CPU, like the important amount is like making this comparison. So it depends how many times we do this comparison. So how many times? So write out the sequence of numbers for an array of size n. What does the sum of all right. So there is a formulation for this type of sequence. So what we should do now is to know how many times these for loops run. So actually, we answered the how many times for our um, outer for loop. Outer for loop is running length minus 1 times, right? So times, so inner loop, as you say, carcass, t-carcass. Do I say it correctly, by the way? Length minus I minus 1. So let's say this is n and this is n, so this is n square. So this is the overall formulation, but yeah, so what is the difference? So we should find the best case, average case, and the worst case. But here, like, it is n square, like our time complexity is n square, but so it says that for pass 1, pass 2, and pass 3, how many times we make these comparisons? It calculates it based like pass wise, like it guides us to do it pass wise. Oh, for first pass, all right, first iteration of the for loop, we iterate this amount of time. All right, let's type it down. Let's write it down. Length, all right, minus I, right, minus 1. But what is I? What is I? I know. I is 0. I is 0 in the first pass. I is 0. So I should, type 0 here. So wait a second. The inner loop. So it asks us how many times the inner loops will run. Inner loop. So all right, I already typed this part, so this is correct. I is 0. The iteration amount is like length minus 1 time. All right. Length minus 1 time. So this is the first pass. And in the first pass, the inner loop will run length minus 1 times. All right. So in what happened? My application got broken, I think. In the second pass, it says length minus 2, and then in the third, maybe it is 0. Now we should sum them up. So length minus 1 plus length minus 2 plus, let's say, length minus 3. So maybe we should ask the formulation for that, because in high school they teach this stuff, but and also, what happened to my program? Let me close it and reopen it again, like open it again. Remind me later. Quit. I guess we can find that formula by ourselves, right? It shouldn't be that hard. It shouldn't be that hard. Actually, like n minus 1 plus n minus 2. So, like, what is the summation formula of 1 plus 2 plus 3 plus 4 plus. So n times n minus 1 divided by 2 is the summation of 1 to n. We have kind of similar thing here, but why does my program got crashed? Let me reopen it again. Come on, man. Is it n square? It should, like, at the end, I guess it is n square, but close. But let's not guess. Let's derive it. You've seen this one on before. Gauss theorem. All right, like in high school. What is 1 plus 2 plus? Yes, like, all right. Yes, closed form of fraction. Do you remember it? Yes. Like a n times n minus 1 divided by 2. Like, this is the whole formula. Yes, that's the exact comparison count. Now turn it into big O. Like this is why I said n square, all right? Big O asks, as n gets huge, what terms dominates? Strip the two things Big O throws away. The constant divisor, does a constant factor change the group? All right. The lower order term. We also get rid of the lower order term. All right. This is the lower order term. Nice. After we drop the lower order term and the divisor, what we get is n squared. So like after this, I'm gonna ask what is the best case, what is the worst case, what is the average case, and how do we do that? And understand why it is not just hand wave. What does hand wave mean? The shrinking end buys you to wow. The shrinking end buys you 2 times constant factor win, but big O eats constants. So that's the real. So as I said before, for all the sorting algorithms, all right, for all the sorting algorithms, they are n square. So like, I mean, if you don't apply any logic, or if you don't apply any optimization on top of them, all of them has nested for loops and like a brute force, and it is O n square. But the optimization part that we use in our bubble sort is shrinking the end. So maybe we can call our live video like maybe we can change the title of our video as shrinking end, like the shrinking end. Like I really like this term, the shrinking end, like a title of a book or something. The shrinking end. Shrinking. So this is the optimization part we have. But since we apply the big O notation, it eats it, right? It what it does? Eats. So but big O is eat constant. So yes. So all right. So the shrinking end buys you 2 times constant. Like, I didn't understand this part fully. Like like what I understand is we earn constant factor win. But since we we apply big O notation, it eats it, so we don't see it in the big O notation. Like we don't see the difference in big O notation, but we have actually. So now the space complex. So for space complexity, if we have an array or something, or if we create or if we store um, then we may care about um, space complexity. But in this question, we don't like initialize or so. I wonder what it says. What would it will say? Look at your bubble sort method. Besides the input array itself, what extra besides the input array itself. Alright. So we don't count input array at all. What extra memory does it allocate as n grows? So as n grows, um, as n grows. I think this is another important thing. Important terminology. As n grows, because like we create our logic on top of this, like as the as soon as the n grows, as the n, not as soon. Let's remove that part. As the n grows, what changes for our bubble sort? Like nothing changed. Let's say 5, 6, 1. We have for loop here. Like the amount of comparison will definitely change. What did we have here? Like a j starts from 0. J goes up until end, which is length minus I minus 1, as you say, Carcass. And this is I starts from 0 and goes up until length minus 1. So this is the length, this is the n, and as the length increases, space complexity doesn't change at all. The end variable, the I variable, the temp variable inside the swap. So does the amount of extra memory grow when the array gets bigger? 10 elements versus 10 million. What's the space? I guess like integer, like how many bytes for integer? Like is it was it 4 byte? Was it like we have integer and we have like a real integer class, and maybe so if we care about the amount of space for our variables, because I didn't think about the space for our variables because they are too tiny, but like I thought about the array because arrays are object in Java. So but if I need to think about our variables as well, because in our for loop, as it said, we apply a swap operation, and actually we have 3 variables and the number of them isn't increasing. I don't know. Does the amount of extra memory grow? Actually, no. We have these variables, these two variable, and an I, and the temp like a 3 variables. So nothing more than that. So I will answer no. It doesn't change. Like we have these 3 variables in each of our iterations, so it doesn't change at all. So most probably it doesn't change at all, and we answer it correctly. I guess now we can continue with heap sort, right? Correct. O1 space. Those 3 variables get reused every get reused every iteration. So this is the verb I should use. Not accumulated, yes. So no extra memory. So time complexity and square. So maybe last question, like should we know like it's worst case, and like for our for interviews, should I know the best case scenario, like a best case time complexity, worst case time complexity, and average case? Like, should we know? Let's see how would it answer, and then maybe we can continue with heap sort. We have some videos. First, I should find the correct one because I created. Actually, we can preview. I guess this is not hippify down. Maybe this one. Left sub-tree, right sub-tree, version 3. So 20 seconds long video. There is something called shift, like a shift down, but shift down, like there is a typo or something here. So maybe we can open it and watch it to understand the animation better. Let me open it here. Maybe I can close the bubble sort animation, move it to let's open this. I click on the wrong one. Open with QuickTime. No, this is this is cadence algorithm. No, this is jump game too. This is something else. Sorry. Let me open the correct one. Reveal in Finder. Open with QuickTime. Yes. All right. Let's see how it works. Actually, I don't remember anything, all right, about the heap sort, but like heaps are trees basically. And at root level, we have, let's say, if it's the max heap, we have the max value, so that each time we need to fetch the big one among the all our input, we easily or in like at O1 complexity we can get it, which is amazing. But other than that, I don't remember anything at all, and the animation doesn't look good either. Maybe we can open this one. Shift down mechanics. We have the code, but I don't want to look at the code. I want to understand the animation, and then by looking at the animation, I want to type we can type the code together, right? Do you guys, what do you know about heap sort? Can you help me a little bit? Like we have, like, if I use subtree, there must be some recursion, all right? Because in my animations, I use subtree term to indicate the function call, and the function returns its answer. We have subtree, and I guess the values are changing. 1, 3, 5. All right, there is definitely the recursion here. So let's talk with AI, chat with AI, and let us guide us. All right, let it guide us. So now I wanna study heap sort algorithm, and I don't wanna hear, I don't wanna see its code or something like that. But what I need is like a, I have its animation. I see that we have like a, some sort of subtree call, and so I guess there is a recursive part in this, right? So without giving me any code, I need you to guide me um, to write, like to type its code. Um, can you guide me? Like I wonder how it will guide me, because mm, like I thought that the animation I have is like was good, but it isn't actually. Like we have, like in the animation I don't see, like the only thing I realized that there is sub 3. So and animation, like sub 3 is now valid heap. So what is the meaning of like a being valid for heap? So maybe it changed the swapping. uh, hmm like there is a, like bubble it down and bubble it up, right? Like that was this convention. Let's see. Tutor mode. I should have said use tutor mode 2. Let's go with tutor mode 1 today for this problem. Good, you got the shift down animation in front of you. Like actually I don't have it. I don't have it. Why I don't have it? Like renders version 2, like in preview, and there are frames over here. And is there the, you know, it would be great if we had the animation. Before we write anything, the confidence audit. Heap sort has two big movements: build the heap, turn the row array into max heap. Sort by extraction. Repeatedly pull the max off the top and shrink the heap. So, like what I understand here is like we're gonna have a heap, like a tree basically, and the max value will be on top. Let's call it 10, and we're gonna fetch this root again and again, and maybe put it, like put what we extract there, let's say into array. So by the end of this extraction, we're gonna have an array like in ascent, like a decreasing order. So I guess this is the logic of sorting, right? But first we need to build. So there is a phase, like there is building phase of this heap and extraction phase, I guess. Extraction phase, right? So like each of these should have their own time complexity, and we need to know about them. And the underneath both sits the one recursive looping helper you saw in the animation shift down. Heapify. I heard this a lot, but I didn't internalize it, so I keep forgetting it. A parent compares with its children and sinks down move. So tell me, which of those three pieces, build, extract loop, shift down, feels solid to you? Any of them? None of them. Which feels fuzzy? So So thank you for dividing the heap sort into parts, because it helps me a lot. Like a build, extract loop, and shift down. This is amazing, all right? But none of the parts are okay for me. So what do you think we should start? Like a maybe build phase? What do you say? So actually it is not build extract loop shift down. Build extract and shift down. So there are 3 phases of heap sort. And also actually update the studying not bubble sort but heap sort. I guess now, yes. Building, extraction, and shift down. Like these are the phases. So here's my counter suggestion. Then you pick. Build phase is tempting, yes, but build is literally just called shift down. Like maybe should I should ask this first. Is this shift down or shift down? Because in the animation I may have typed it wrong. First we need to make sure the the terms. It's shift down. Shift down. Oh my god, I learned it now. I learned this now. Shift, not shift. Why? Shift, how is it called? It's like shifting the floor through a sieve. The element trickles down through the layers. You'll also see it called heapify, sing, or bubble down. Yes, in different textbooks, all the three, like all the same operation. Shift down is just a common type. Oh my god, shift down is typo. I knew this like as shift down, but it is not shift down. Like how is it called? First I should know like how is it called? Give me its phonetic alphabet version. IPA. Lift, gift, sift. Is it sift? So sift down, set like a 2 normal English word. The I is the short I, bit sit, not the long E. Now the sifting. So that's wonderful. It is not shifting down, but instead sift down. So the question we had, sift down in a loop. So building phase is kinda easy, I guess. It tries to say us. The end extract is also just called sift down. So sift down is the atom. Both bigger phases are wrappers. All right. So the term wrappers is quite important for us, because in like while building projects or while learning algorithms, there are some core part like the atomic part, and also there is like a wrapper part. Like understanding both is quite important, but the atomic part is more important. All right, so let's start with the atomic part. Sift down. First thing sift down needs, the array is a tree. Yes, just flattened. All right. A node sitting at index I has a left child and right child. Yes, actually they're even like I know their formulation as well. Like if it is I, 2 times I minus 1 is the left child, and 2 times I plus 2 is the right child. So like this is left and this is right, and for 1, for I I equals 1, the 3 is left, and 4 is it's right. All right, let's continue. Question before any code. So let's start with sift down. Sift down. First thing, yes. Question before any code. If a parent is at index I, what index? Yes, we know this. The formula is 2 times I plus 1, and like this is left child, and 2 times I plus 2 is the right child. What time is it, by the way? Yes, all right. Yes, this is the formulation. Like this is the representation of a tree using an array, and this is the formulation. These are the formulation for the left child and for the right child. Like knowing this formula is quite important, all right? Because without knowing it, we cannot. It also calculated the time. And yes, left is, you know, this one, and right is this one, and that's the whole array as a tree trick. Yes, locked in. Now the logic inside sift down. So our goal right now, like maybe I should type, we are studying heap sort, but let's say understanding sift down method. Set the label and continue, and maybe move it a little bit up. Sift down method. Emma, you knew what does it say? Now the logic inside sift down. In the animation, the parent looks at his 2 children. Something gets decided, and then maybe something. Among the 3 nodes, parent at I don't know, man. What does it say? Describe the rule inverse. Don't write the code. I didn't understand what it asked. In the animation, the parent looks at its 2 children. So, oh, all right. Now I remember one more thing about heap sort. So parent looks both its children, 5 and 7, and picks the smaller, or I don't know, the higher, but there's a rule for that. So we look at 2 children and decide which to go into. All right, something gets decided, and then maybe something moves. Describe the rule inverse. Don't write the code yet. So I, like, after you said that the parent looks its children, it's like both of its children, I remember that there is a logic for picking the direction, but I don't remember exactly which direction was it for. Like a let's say we have a max heap, or let's say we have max. So does the parent go into the, you know, picking the smaller one or the higher one? I don't know, like I don't remember at all. Or let's assume we have a min heap. So which direction the parent picks? I guess there is a logic for that. And can you give me a hint or something so that so that in the long run I don't forget. All right, because if I internalize the logic, I don't forget it at all. But if I memorize, I keep forgetting it. All right, but thank you for the hint. All right, because now I see that, now that I see that, like, parent picks the lane based on the comparison. So now let's wait the answer from the AI, and also maybe while studying that, maybe we can also create animation for that. But for some reason, Safari graphics and media. What happens with my Safari? Can I close my Safari? And let's see, because I don't like my computer runs its fun to cool it down. So it answered. So great instinct, let's make it unforgettable. Unforgettable instead of memorized. Yes, I would glad if we make it unforgettable. The invariant of the max heap is one sentence. Parent must be bigger or equal than both children. All right. Alrighty. So imagine, let's pick a different color. Imagine like we have a tree. All right. So the rule, like the invariant, like the term invariant is also important in variant, I guess, because the rule here is like for max heap is that the parent is, let's say, should bigger. Like does the order matter here? Like maybe left child, maybe left child should be 9 and right child should be 8, or like but it says the invariant is like parent is bigger than both children. All right, let's continue. The invariant of max heap is one sentence. Parent must be bigger. All right, that's the only rule. If it's only rule, then the location of left or child, or the the difference is doesn't matter. So we can place the 8 here or as a left child or right child. So now reason it out. Say parent 3 and children is 9 and 5. The rule is broken. Yes, the rule is broken. You are going to swap the parent down with one child. Which one? I guess it is gonna. Which one I should like? Should I am I gonna pick? Would I pick? So it said that the parent is 3 and the left child, let's say 5, let's say 9, and right child is 5. So it is a max heap, and now the rule is like a broken. And which one I should which one would I choose? Like I don't see any difference picking 9 like a left subtree path or a right subtree path. Which one? Actually, let's iterate. All right, if I use if I pick 5 here, what would happen then? 5 here, 9 over here, and 3 over here. So parent is bigger than the right child, but it is not bigger than the left child. So now we can, let's say, not substitute, but we can conclude that we should pick the bigger one. All right. So now, instead of memorizing, I thought that if I tried out and see it by myself, I would learn. So now I tried it by myself. So I picked a root is 3 and the left child is 9 and right child is 5, and I picked the right side because I didn't see any difference between picking 9 or 5. So I picked the 5, but then what we end up with is not a valid heap, because now my root is 5 and left child is 9 and right child is 3. So like the rule is still broken. So now I guess the correct way is picking 9, like picking 9. But then another question emerges. All right, what would happen if we have, let's say, not 9 but 4? Again, we would choose 5 because 5 is the bigger child. But let's say we have let's say we have 2 and let's say 1. So in this case, it is already like rule is sufficient. All right, rule is good. But like is there a case where I should keep going even though I have a valid heap? So in this case, our heap is valid, but I'm just asking. So what do you say? So now I learned that in max heap, we pick direction, because I guess we are using like a recursion, and we need to pick a path, either going into left child or right child, and the decision is made based on the comparison, and we should pick the bigger one. So if it's a max heap, we should pick the bigger one. All right, so maybe I can code it like this. So you just derive the whole thing by breaking it yourself. Thank you for that. That's exactly the move. Promote 9, done. Oh, it is promoting. All right, that is awesome. Promoting. So like 3 to like a 3 9 5. Let's say 3 9 and 5. So we are promoting. We are bubbling it up, in other words, or heapify, or or something else too. We are in break. Let me check. All right, streaming. Let's click on view. All right. All right. I think that seems legit. Actually, I should change the color. I should make the color like a golden hour. Yes. Um, all right, this seems good. Let's like it. Wonderful. You just derive the whole thing by breaking it yourself. That's exactly the move. Promote 9, done. Now your real question. What is my real question? It's the sharp one. Is there a case where I keep going even though the heap is valid? Yes, this is the question that I want to learn. Flip it. All right. You don't keep going because it is valid. You keep going because of the swap you just made. Watch. Say the tree is bigger than 3 nodes. What does it mean? The tree is bigger than 3 nodes. Like parent 3, children 9 and 5. But 9 itself has its own children below it. Say 7 and 6. All right. You promote 9 to the top. Good. Top is fixed. But Where did the 3 go? It got pushed down into 9's old slot. Slot. Now sitting above 7 and 6. 3 is smaller than 7. The rule is broken again. One level low. All right, all right, all right. So we are, let's say, navigating or passing our problem to children. All right, not transpassing, but passing our problem. The rule is broken again. One level low. Like I really loved this. All right, I really love this term. So maybe we should type it down. All right. So the demoted element, demoted element 3 keeps sinking until it land. Oh, all right, all right, all right, all right. Now it makes a little bit more sense. Like imagine we have a tree, like a good tree, all right, and somehow, like somehow we put wrong number here, all right, and let's say this is 9 and 5. So we pick the, I guess, bigger one, I guess, all right. So we pick the biggest one. So let's say we promote 9 and we push the 3 down. But in the new slot that 3 is in, it is not good, because let's say we have, let's say, 6 or 7, like 6 and 7, and now 3 is not in not good position. So we need to bubble it down a little bit more. All right. So this is what I understand. All right. So the demoted element, like a 3, keeps sinking, keeps sinking. All right, all right. So it keeps sinking. So it goes down, down, down. By the way, what was my question? I don't remember, but let's continue. So that's the recursion loop, like a recursion or loop you saw in the animation. The like 2 stopping conditions, no stop. Like when, like if the heap rule is valid, we don't keep going, all right? Because I asked that, let's say we have 9 6 7, like a 6 7, but let's say we need to bubble down, is there a case we need to push 9 below? But I guess there is no case for that, so we are safe. All right. Like 2 stopping conditions are when the parent already bigger than their its children, we don't swap. The second, hit the button, like this is the edge case or base case. All right. And the beautiful part, the trust your animation is named after. When you stop, because no swap needed, so you trust that everything below is already valid. This is interesting. You don't recheck it. That is interesting. So tell me in words, after you swap the parent down with the larger child, what do you do next, and from which index? So let's say I had 3 and 9 and 5, and 9 has, let's say, 1 2. All right, this is the 3 I have. Parents should be larger than, right? All right, this is a valid, not valid, because we need to swap. So while swapping, we pick the big, let me copy this. All right, like while bubbling down, we pick the larger one. So we pick the 9, we swap it, we promote to 9, 3 9. All right, this is all right. After changing, what do we do? I think this is what it is asking, right? This is 3 and this is 9, and this is a valid heap. So what it asks? What does it ask? So tell me in words, after you swap the parent down, like a after you swap the parent down with the larger child, like with the largest, like if we are like if our hip is max hip, we pick the larger, like a while we are going down, we pick the larger one. So all right, what do you do next? Like what do I do next is like a maybe checking if it's valid, like if it's like if the left subtree valid from which index. We continue ship down from the index where the parent landed. Parent landed. Yeah, yani şöyle, maybe we can say so we change like we swap like a 9, like a we promote 9 and we pushed 3 down, and now we should keep going from the node like from the new position of 3, right? Let's say it like this. If you guys have any question, you can ask me and we can think about it together. I may not have the answers, but we can, you know, study together, create animation using Blender because it is a amazing approach. All right, because visuals help a lot. All right, at least we can do this together. Exactly. You promote the larger child. Yes. The parent sinks into the child's old slot. Yes. And you repeat the same operation from that new index. Yes. You repeat. Repeat after me. Same logic, one level down. I should type it down, man. Same logic, one level down. Same logic, one level down. Like, this is cool saying, all right? You now have the full mental model. Time to write it. Open your sift down method. I don't have a sift down method. Before the body, the signature. Yes. Think about the information sift down needs to one thing. Huh. Alright, like it asks us that we have a sift down method, and what would we do? Like our goal is like finding the larger child, finding the larger child. We are the parent and we have our, let's say, left child and right child, and since we are in array form, I guess what we need is just an index and the array reference, and I guess that's all, because the remaining part is just the logic. So let's say left child, like a let's call it left index, or this is fine. Left index is like a index times 2 plus 1, and right index is left index plus 1. Left index plus 1. All right, so we now are like a left child's index and right child's index. Now I guess we should find the larger one. So how do we find the larger one between two elements? Let's call like a if array left is bigger than or equal than what actually? Than the parent, right? No, like if we are like if this method called, or when this method is called, the heap is not in a good place, so we need to make it in a correct form. So so only thing we need to do now is like finding the bigger one. If like a if the left is bigger, then we go that way. So we um, we actually swap, but do we need to call the recursion? We need to swap like a index and left index, right? Let's think about it. So all right. So if it is not like as, we should swap parent with with the right index, and then maybe it may need array reference too. That's all right. But I think since it is shift down method, we should we should make it recursive, right? We should make it recursive, guys. But where can I make it recursive? So like after, let's say after swapping, all right, we had, let's say 9 6 3, so we pick the bigger one and we swap, we promote, no, like this is 9, no. Let's make it 9 and let's make it 6. All right, so we promote 9 and push the 6 down, and then what? So and then our next problem, our next sub problem, actually, like a sub problems, like terminology of sub problem is quite known, all right, in dynamic programming questions. So we, let's say, delegate our sub problem, our problem, to our children, one of our child, all right. So and now I think we need to call like a recursive function. Like our function is shift down, and after we do this swap operation, then maybe we call like a shift down with different values, with different variables. So our root changes. So our root is now left index, probably, like our root index is left index. And what do we need? Like array, maybe we can give the reference of array. So like it is same here as well, like we make the swap operation, I mean we swap operation, and then we need to call our function recursively, shift down right index. I guess that is correct, most probably. I mean, at least for the shift down, which is essential part, like essential part for our heap. I mean, heap sort. I mean, we are not at the phase of sorting right now yet, but what we do is like validating our heap each time. After we do some swapping operation, we learned that we do this swapping operation based on picking the larger one among our children. And after we do our um, swapping, we do like we call our recursive function. We delegate our problem to our children, the bigger children. So where are we? What did it ask actually? Signature. So let me, explain what we have completed. So now the function I have, like we have, is like we have shift down method. It takes index as a parameter, like an integer, and then the array, like arr, and inside it we calculate the left index. Like left index is index times 2 plus 1, and right index is left index minus like plus 1. And then we have if condition, all right, and we compare the value at index left in array. If it's bigger or equal to the value at right index in the array, if the left is, if the left child is bigger, then we swap the, we call the swap method, which is its first index is index, and the second parameter is like a first parameter is index and second parameter is left index, and we call our recursive function shift down, like shift down, and we give like a left index and array as a parameter. And in else, we call the swap method again with index and this time right index, and then below it we call like a shift down, like our function recursively, and we give like right index and comma array as a parameter. And I guess this is it. This is all for the shift down method. Are we like is it correct? So let's see how is our AI gonna answer or respond to our message. If you guys any question, you can ask in the chat, and we can, let's say, discuss about it together. So let me hold the structure up against the model you just built. I'll pick the one thing that matters most and we trace. Yes, another word I liked, trace. Take a tree that is already valid. Oh, I guess it pushed me, like it pushed our code to the case where it doesn't, function properly. Now run your code on it line by line out loud. Left, right, computed. Like if the left if the left is larger than right, we go the S. You swap 9 and 5. Stop there. Your cut just swap 9 down. Put by, all right. What did your if forget to look at? That's wonderful. So we have a missing case, like a missing case. So zoom in. So I just compared the, like I just find the bigger one among our children and go that way immediately without verifying that even we need to do this or right or not. So I guess the first condition would be if we need a swap or not. So this is the first thing we need to think about. So we need to check that if our root is bigger than our children. So if it is, we don't need to do this at all. So maybe what we forget is like comparing our parent with his children, and if both of them like is like a higher or equal to the parent, then we don't need to make our recursive call. So yeah. That's the fix. But while I was like we were typing this method, I thought that if this method is called, then we need swapping. But I guess the AI didn't know what I had like we had in our mind. So maybe maybe we can say it. All right. Um, let's say it before, and then we can read the answer it says. So actually, while we are writing like a typing this code like a sift down method, we thought that if this method is called, then there is absolutely necessity for swapping, and if we don't need swapping, then we don't call. So in the algorithm we have like a we would have another if condition that says us that indicate that indicates us that we should do like the current position of heap is not valid, so we call this shift down method. But if it's valid, then we don't call it at all. So I had like we had this in mind. So I guess our code can be correct, right? Let's press enter, and while it's answering that, we can read what it already told us. That's the fix. The parent has to be in the comparison. If the parent already wins, you do nothing. No swap, no recursive call. That's your stop condition. So the cleanest way to handle parent versus left versus right and the stop condition all at once is to stop thinking left versus right and start thinking who is the biggest of three. This tells us something different. It says that what is like who is the biggest among all of these three elements. So instead of comparing the children between them, but I guess it is one of the ways of doing that. Here's the idiom: try restructuring around it. Start by assuming the parent is the biggest. Make a variable, call it largest, and set it to index. Then ask two questions in turn. Does the left child beat the current largest? And does the right child beat my current largest? All right, all right. That's another way. That's another way. After those two checks, largest hold. I guess it is the better way because like I see this variable in different places. All right. Like in jump game, like a jump game two, and there was a like a circular game where like we had our fuel, our tank. Well, what was that question? Like it was a greedy question. Um, it it were asking that which point should we start from to complete the tour, giving that given that um, you should have positive amount of net tank to to continue or start. Yeah, I mean continue continue forward, continue going forward. uh let's continue what it answered. I see your reasoning. Shift down only gets called when we already know it's invalid. Yes, so it's safe to always swap. Yes, that holds for the very first call, but it falls apart the moment the method code is. Oh, wonderful, 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 wonderful. Like this is correct, man. I mean, like I thought that. Oh my, like I thought like iteratively and create a recursive function. that is that is absolutely correct. Because when we call the recurse when we call our method recursively again here, then like we don't, maybe then we should here put I mean above the recursive call, maybe here we should add um at the if condition, uh, if we need to continue or not. And same condition here too. If we put these conditions here, then our recursive function would be okay too, I guess. Your shift down swaps and then recurses down into the child who checks whether position is valid before the recursive call fires. Nobody. All right, all right. So the element keeps thinking, swapping. All right, all right, all right, all right. So the stop condition has to live inside sit down. Here's the why the largest idiom is so clean. It gives you the stop check for free. All right, all right. Let me give it another option. So I have another idea. So like before calling our recursive function, what would happen if we like have a if condition or something saying like a checking or verifying that after swapping if the heap our heap is valid or not. If it's valid, um, then we don't go recursively again and again, and we should put this if condition above the first recursive call inside the first if, like a if, and in our else statement, again above the shift down method, we can add another if condition, checking that if the heap that we have is valid or not. So would it be all right? Uh, so 20 minutes left. So I guess in the next session I will be working on Python. So in this session we studied bubble sort and heap sort, and we realized that heap sort has recursion, and actually like a merge sort has recursion too. I don't remember quicksort fully, and selection sort I guess it was fully iterative. Bubble sort is iterative, so heap sort is recursive. Like heap sort is absolutely recursive because it is array version of tree. So if a tree is included, so then most probably it is like we're gonna use recursion, all right? So your instinct is right. A validity check that gates the recursion is exactly what is missing. You are just placing it in the wrong. We are placing in the wrong spot. I didn't think about it. I thought I completed correctly. One step too late. Two refinements. Put the check before the. Actually, while I typing that, I thought it, but I said I think this is the correct one. So it says that not above the like again above the function, like above the recursive call, but even above the swap operation too. So let's say you but actually there is a actually there is a difference. I put the if condition over here explicitly because um, if we applied swapping after the let's say after the swapping, if the heap is not valid, um, what should we do? Like after swapping, so let's type it, all right? Because I did it explicitly, man. We have 5, 9, and 7, right? We picked the bigger one. We promote it. We push the 5 down. Actually, here we are applying the swapping. So it says that before the swapping operation, you should first check. So we get the left index and right index, and then like if we have condition here, like left is bigger than the right, and also we need to have the second condition as well, like because um like left can be bigger than right, but if we don't need to swap it with its parent, so there is no need to call recursively, all right? Because to call recursion, you first need to you like apply swapping. So um, I mean, first we need to do swapping, all right? And if I apply the swapping, so like a swapping and recursive call should run together. If I apply the swap, then I should definitely call the recursive call, because then I may um, after the swapping, like is it 100% guaranteed that after swapping we should call swap? Yeah, I mean we should call our recursive call. I think like this is important. This is important because after the swapping we may not need to continue recursive call, but it depends how we structure our recursive call, all right? So our current version of our recursive function is like a first checks if the left is bigger, but it is not only condition that we need to check. Like if it is invalid, I mean invalidity, I mean if it's the word. So if we check the heap is valid or not, if it is not, and then we then compare. So but I thought that we can do it like a outside this function, so that it is guaranteed that the heap is invalid. But and then AI pushed back and said that since you are building recursive function, after the calling in the next stack frame, you would need to know, you're gonna have to know uh, it should call it recursively or not. So we need a if condition there, but and then AI said that still this is a not correct condition, so you need to apply the swapping based on that if condition. So we need here. So and then we said that swapping and calling function recursively should behave as a packet. So if one happens and then the second happens too, so um, our recursive function, all right, and we like let's first control, or let's first check if invalid heap. If it is invalid heap, then we can compare the left child is bigger than or equal to right, then do our swapping operation, and then calling our recursive function. And in our else statement, we do again the swapping operation and then the calling recursive function with different values, obviously. But I'm now trying to understand like where to put these, like an invalid heap, or how can we. Let's continue, right? Because the 15 minutes left. Put the check before the stop, not after. Check at the top of every call. If the position is already valid, You stop before doing anything. No swap. All right. No swap, no recursion. No swap, no recursion. So let me write it down. No swap, no recursion. So it also validate valid. It also makes it valid that our idea is correct. So swapping and function is um, is working together. All right. Here's the key realization. The check is the position valid, and the question, who is the largest of the three, are the same question. Look, all right. You build largest. Assume parent test left, test right. Position is valid. Literally means the parent was already the biggest. Yes. Position is broken means using this variable we hold the information of whether we need swapping and recursion or not. So I tend to see variables as informations. So this is the information, all right? Information that tells us if the position is valid or not. So based on this information, we apply our logic. If the position is broken, means a child with the parent. So you don't need a separate validity. Yes, it is a word. We learn it. That's wonderful. If so you don't need a separate validity if and a separate left and right if. It collapses into one comparison. So the shape becomes, I think we can build this algorithm on top of our logic too, comparing this one. But does it say that we don't do this comparison at all, or we are doing it in using another variable? I didn't get that part. Compute the largest. So I guess using another variable. So using this variable, this magical variable tells us if it is invalid or valid, and it also gives us the largest element, so that using only one variable we a complete lots of things. All right. Complete largest parent, then test this, right? If the largest equals index, so largest is something that holds an index. I mean, I thought that it is not an index, but the number itself. But I guess if the largest equals index valid, stop return. Else, so this is smarter way of doing that. Let me tell it this. So thank you for your smart move, but as a human being, I first should come up with an idea, like a basic or simple, even maybe wrong in some cases, but working, valid solution. So instead of showing me this polished code, all right, validify my approach and give me the whole code, all right, based on my approach. I mean, in my approach, I have a sift down method, and I compare, I find the bigger one, all right, a bigger one between the left and children, and I learned from you that first I need to check if we need swap or not. So inside this if, I have we have another if, all right. We are doing this if condition to check if we need swapping at all. And in else statement, obviously we have another if statement on top of swap and shift down, all right. And this tells us whether we should swapping or not. So can you give me that code, and also like I don't need the polished code, all right? Because during the real interviews, first thing that I can come up with the basic version. So validify our approach and give me the code. Let's see how how will how will it answer. Because like using this largest variable is a wonderful way, all right? Because like this largest is like a gives you two information. One, whether you need to do swap operation and keep continue, and the second one is like a which direction you should go. Like using one variable you can do like a like it collapses into two things. Like I mean it collapses into one comparison. uh, but during the interview it is not possible. Like if of course it can be possible, but it is hard to come up with this polished optimized version. So I should first, like we should I should first get the core logic and make it unforgettable. All right, you're right. Let me honor the oh thank you, man. Let me honor the request. And first, your approach is legit. Thank you for that. It's not the worst version. It's the other standard way to write sit down two schools. All right, give me my school. All right. Largest trigger. What I was nudging. Assume parent test child against a running. Like this is. I know this is the better way. I know this is the better way of doing that. All right. But uh, let's start with this one and then continue with the uh, polished one. Wonderful. Both are real. Both are real. Yours reads very naturally. Here it is, written in your structure, Java basic version. No, no cleverness. Yes. Sit down, calculating the index, left child, right child, the bigger child, and we compare the left with the current, like a current element, and then if what? No children at all, nothing to sing. Like how on earth does this mean no children? Left is bigger than n. So else if right is bigger than n, only a left child exists. I don't understand it all, man. Both children exist. Your idea. Compare. Like don't give me the base case, alright? I wanna think about them later. So this is our case basically. Left child is bigger than the right child, then bigger child. Oh my god. It is doing the same thing as it has said. Do we even need a swap? Your validity check. Yes. If like this is the index, right? Bigger child index. If the bigger child index, oh my god, I don't understand that part. Guys, I think I'm gonna stop and take a break now. Thank you for joining me today. In the next stream, I will be working on Python. I will study some Python, learn its syntax. I have a project, ERP project, and I coded it using Cloud Code, and now I study its components so that I learn its syntax. But let me, like, we have 6 minutes left, so like I have a little time left until I finish my stream. So like the code you gave is not the code I described to you, all right? Just like don't add the edge cases check. So what I need is like a sift down method that takes the index and the array itself, and we calculate the left index and right index, and then we have an if condition that checks if the left child is bigger than the right child. Then Inside this if condition, we have another if condition that tells us that um, if the heap is not valid at this root level, and if it's not valid, we do swap and sift down. Oh, welcome. Like I'm studying heap sort algorithm. Heap sort algorithm. Like it is asked during the interviews. I need to know like it's how well it runs, how well it sorts, like its time complexity and space complexity. Now, like we are studying its implementation. During the interviews, like the implementation detail is not asked mostly, but it is good to know. So that's why I study. So in 5 minutes, I'll end the stream, but thank you for stopping by. So actually, the part was on. So yeah, I will stay away from this until I learn. So if you don't know coding at all, like this seems like a quite hard. Um, Even for me, it seems quite hard. But I spent lots of time on trying to understand these algorithms, quite time. So now they seem a little bit, let's say, easier. All right. So let me dictate. So like the code you gave includes the parts that I didn't mention at all. So give me the code with this only, all right? Sift down. Like this method takes index and array, and inside it we like calculate left index and right index, and inside um, we have if statement, and it checks the left child and right child. If the left child is bigger than or equal to right child, we do swapping and calling our code again. And but above the swap and sit down, we should have another if condition saying that if the current heap is valid or not from the perspective of the root. All right. And the else statement of the outer if, we have like a we have another if statement inside the else saying that if we need to do like a swapping operation or not, all right, if the heap is valid or not. And inside this if, we do swap and shift. So give me that code and verify. I'm using cloud code, and for AI's model, if you ask AI model, it is like it is local model actually. Let me check its like it is voicing and the models. The model is I guess large V3 turbo. Large V3 turbo. Yes. This is for dictation and it works quite well actually. Instead of typing each time, I use it. Um, all right. I think there is no background song. Why? What happened? I don't know. In OBS, I don't see any system audio, but it is okay since I'll end the stream soon. So here's your structure. Exactly you as you described, nothing added. So we compare the left child and right child. I know. I want to run one too, but mid end computer. Yeah. So my computer is also runs its funds. Actually, I don't know. Like OBS uses like a 6% of CPU, and I have only one Chrome open and nothing more. But somehow, like it uses lots of CPU. Like we better have like a more RAM and CPU power. I don't want to disrupt your maths. Thank you for that. So I got a little bit tired too. I will take a break, and then in the next stream I will study Python. So thank you for stopping by. Thank you for your good vision. Thank you. Um, so now it has written the code that I described exactly. In a if, do we actually need to swap? Like if the left child is bigger, yes. But actually, this is not what I meant. I mean, like the parent could be smaller than left or right. In both cases, we need to swap and sift down. If the left child is the bigger one, I don't understand. Let me do this too. So the algorithm is sound. This is faithful working sift down for any node that has two children. One honest node from the verification, I'm flagging it, not fixing it, because it's exactly the kind of thing you reread past catches later. This version assumes what actually? Assumes so the algorithm. Oh my god! Like the another downside of using cloud code is like this UI thing, but verification of spine. Yes, this version assumes array left and array right always. Alright. I do that at a leaf or a node with only a left. Like I don't care this now, man. Come on. Like the thank you, but the code you gave us is not exactly I described because like what I mean by understanding if we need swapping or not, I had this following in my mind, all right? I thought that if either left child or right child, like any of children is bigger than the root, then we should do swap and sift down. But you only compare it with left children. Like, hmm, all right. I see now. So um since we are in this if statement, we already said like left is bigger than right. So if the left is bigger than the right and the bigger than the root, so then we should swap. So it like here we don't need to check if it is bigger than right because we already done this. We already done this. So in the else statement, right child is smaller than left. All right. Uh, Smaller than left. Smaller. Like in the else statement. In the else statement. Uh, like in the first if we check if the left is bigger or equal. So in the else, the right is bigger, obviously, bigger than left, bigger than left, bigger than left, bigger than left. Let me see it. All right, bigger than left. So we have bigger than left, bigger than left. So for it to be invalid, we need a smaller one. So all right. So in this case, we check if the right child is bigger than index. Yes, of course, because like if the right is bigger, then we also check if it is bigger than the root as well, because checking only the uh, compare like comparing only the children between them is not enough. We also should compare um, the child with the root. If the root is smaller, then we should swap. So this is what I had in my mind. So it is valid, and so oh my god, the the dictation was on. So let me delete it. And so Feynman check. Why does this recursion stop on its own? That's a good question. Let me check. It stops because like it stops because if none of them, like any of them, any of these conditions are not uh, valid, then we don't call the recursive call at all. So we automatically stop. So because our recursive calls is depending on the if condition that assumes parent, like assumes heap is not valid. If it's valid, we don't make recursive calls at all. This is the answer. Like this is the Feynman check it asked. And then let me check. Let me check. Yes, but like this is the validity check. Yes, this is the validity check. This is the this is for finding the bigger one. All right. So thank you. And now I guess we completed the sift down phase, but heap sort is not completed right now fully. So what are the remaining two parts? So um, can you teach me them fast because I want to take a break now. But before that, I want to complete the heap sort and understand its time complexity and space complexity. So I guess we are done with the core part. So core part is understanding sift down. So hi, are you working on for org or just learning? What does org mean? And um, I'm actually preparing for incoming interviews, and they ask, like common leetcode problems. And I learned that it would be great if I know the time complexity of, these common sorting algorithms, but I cannot memorize them basically. So I need to learn their implementation. Organizational company, yes, all right. I thought it too. No, I don't work it. I'm preparing for interviews at the moment. Um, yeah. So I applied like a few companies, and I realized that they ask these difficult problems in the first phase, and I failed at and a few of them. So I realized that I want to um, make this algorithm understanding solid, and then I will continue applying for new jobs while waiting uh, their answers from other companies. I know that knowing their um, you know time complexity and space complexity is quite crucial, especially for these sorting algorithms. I don't know, man. I'm from the data field, and it is so overcrowded. Um, so like yes, like do you mean software engineering or the I'm from the data field. It is crowded, so the competition is real. So that's why I'm working actually. Like especially with the AI. Like if I had a company, I wouldn't try to hire that much of junior engineers if I don't have future plans, like a long run plans. But instead, I would get some seniors and give them AI and complete the job. Um, Maybe hold a couple of juniors for the long run, but yeah, it is crowded. But I need to earn some money from this field. Um, what you nailed today? You drive, sit down, direction and stop condition yourself instead of memorizing. That's the version that wants yes. When do you when you come back, two things are waiting. Hand type to build. All right, the different boundary things. Like I don't care about the boundary fix, but instead the remaining two parts, which were data analyst, this crowded. Yes, I started learning data engineering. I am the final year of my bachelor. Oh, wonderful. I started learning data engineering, and so like actually like me and you also we can count ourselves as a lucky ones because we are in the beginning of this AI era, and I think we can make use of these AI tools, and also another important maybe the most important thing is having good friends in your college uni. All right, this is quite crucial. um, do you have like a close friends, maybe 5 or 10 of them is needed in the long run? And I guess one of the most important thing that uni provides is knowing these people, close friends, friends that you enjoy being around them, so that because you can build projects and maybe jobs together with them. Building extraction shift down. So you said that the one phase is sift down, and the another one is building heap and the extraction for our heap sort. Three phases. So can you quickly summarize those parts and show me the overall structure a little bit? I think because we completed the hardest part, but still the heap sort is not completed fully. So I wanna complete fully without taking a break. um, and final year is also quite hard actually. I wish you good luck with your studies because in computer science it was quite hard. The last year it was the hardest one. Lots of project quizzes, homeworks, projects, term projects, monthly projects, and then the finals. It was it requires dedication. All right, let's assemble the whole thing. You already wrote every piece. Every piece, here's how they snap together. The three rows, one line each. Sift down, sync one wrong note to its correct. Yes, yes. We completed this part. We completed this part. Build. Turn row array max heap. That's interesting. So if you are lucky with the AI era, does this make me extra lucky? What do you mean? Actually, yes, it should. It should because I create an agent, all right, saying that search this on web, all right, or let's say search this on forums and find me some helpful resources. So it searches among, let's say, 300 pages and find the correct ones, and I read them, and I use my in my project. So even being able to make this type of search fast is enough to be feel lucky, to feel lucky. All right, I will finish my first year next. First year. Oh my god, you are too young, I guess. I guess still, yeah, yes, we can count you as lucky too. But I don't what would I don't imagine what would happen primary school, let's say high school. High school is kind of right, but primary school, middle school, like the we should change how we educate them actually. All right, because um, memorization part is over. We need to, for me at least, we need to learn the concepts. We need to internalize the concept and leave the memorization part complete to AI. That's why I study leetcode, and I need to I want to grasp the idea of these algorithms, because once you learn one thing, you can apply into another thing, because a recursion part is quite important. And I spent months of for understanding recursion, and finally I can visualize engineering techniques first year. Wow, wonderful, wonderful. So yeah, as I said, it helps you search tons of pages. Quite, brother, we live in the same country. Like, are you living in Turkey, like in Istanbul? Han Sohai, welcome. I'm actually studying my data engineering portfolio around the browser game. It's a logistic economy space simulator browser game. Browser game. Oh, so like, do you use like, are you using JavaScript or something? Like since a browser game, but you are saying that data engineering portfolio. So what sort of game is that so that it helps you build data engineer? It should have lots of data or something. Oh, you already said it. It's a logistic economy space simulator. Wonderful. Like, do you use AI that much, or how you structure your project? I mean, or at least how long you've been building? Have you building this project? Answer high. Answer high. So, um, turnover. So, like, we completed this shift down method. So, as we find a heap that we need to move, like we promote one children and push the root down. So build phase is like turn row array max heap. Like this is loop shift down over none leaves bottom up. Extract repeatedly pull the max to the end. I guess I should check the code, but before that, do you guys hear the sound? By the way, I guess you are not, right, because in my OBS I don't see, green. It has lots of data spreadsheets. I'm starting with collecting the data first. Yes, yes. I heard that there are some websites like a resources that you like a you can get the data as zip file and use it for your own purpose. I actually have previous work experience as a Java developer. Wow, data engineer. I just don't have a personal project for that. Actually, like I'm also building personal projects. I recently started game development as well because for object oriented uh, programming, I realized that during college I learned little because all things were um, like from books, all right, not a real world implementation. So in game development, in C Sharp, in Unity, I use lots of object-oriented programming concepts, and I'm quite happy with them. So what I'm trying to say is, like learning certain stuff, you need to pick certain stack. Like if you want to learn object-oriented programming, develop a game, all right. So if you want to learn lead code problems, first make sure you learn like recursion very well because without it, you don't have any chance with backtracking. All right, I don't count DP at all. All right, backtracking, recursion, trees. All right, there is no way, and and graph. All right, this is the hardest part, and they're all built on top of recursion. So and in most of the videos on YouTube, almost everyone explains this wrongly. All right, they show you the stack frame, each stack frame. Like even they build animations for teaching you recursion, and they show each stack frame. But this is not the correct way. And you may ask, where did you learn this? I learned it from a book about the recursion itself, written by a professor in a university. I can find it for you guys later. So I learned it there. So yes, maybe neighbors. I didn't read the caption. By the way, don't forget to turn off the tracks in OBS or actually I'm using like a stream beats lo-fi. So I guess it is yes, it's copyright. So but thank you for saying that. That's why I picked the copyright free version. Bro, you can try out compilers and interpreted project if you want to apply DSA to real world project. Uh, so like, can you give an example? Like what sort of project would I be building? Like a compilers and interpreter. What do you mean by that? If you want to apply DSA, if you want to apply DSA to real, actually most probably yes. Let me let me write it down. um, another good way of applying DSA is like a building, as you say, Hans Sohai, as you say, building like a fundamental stuff, like a SQLite, for example. As you know, SQLite is like a written in Army. Actually, most of the technologies we are using is like a development for Army purposes, but and maybe Git, and then maybe building note taking, like a not taking application, but essential. So if you build uh, fundamental essential things, as you say, because the SA part is used in that level of expertise, let me say, because while you are building a website, like let's say Java Spring Boot, all right, you don't uh, you don't use that much of DSA. You already use the written methods, as you say. Definitely, I agree with you. Um, let me let me check this part, guys. Can you do you are you like do you hear the sound background sound, by the way, guys? I guess you don't, right? Like example, my old project, I trusted JSON to SQL. Yes, sure. If it is a GitHub repo, you can. Yeah, yeah. So building those sort of projects is helping DSA. Yes. In college, in uni, um, like our professors wants us to implement some sorting algorithms or some array functions in C, because in Java you can use array.sort, and it is already sorted, but its implementation is a little bit different. I will read the chat again a little bit in a minute. I need to read this part, but you can paste your project's GitHub link. But if it's a GitHub again, so we have three phases in this heap sort. We completed zip part, zip down part. Let me read the code. So this is heap sort algorithm. All right. So we studied this part basically, and we have another swap here too. So phase one is build max heap. Hmm. I think we need to do another session for max heap, because building it is a step, extracting it is a step. The part we studied is just the sit down. All right. Two things to notice now, that it's whole. Sit down is called from two places. Hmm. I guess we need to do another here, bro. I think we need to do another stream for I did this for my previous company probation. It's nice. Secularize parser. Let me open it. The API implementation will be based. Highlights of project. Recursive print JSON node. I guess you applied recursion, right? Working complex. So, actually, it is this is was before AI came out. Yeah. So yeah, yeah. So actually, in a mid-level job applying, I mean, there was an interview for mid-level, and they asked creating uh, like understanding if a JSON is like, the question was finding the empty slot in the JSON file, and where we don't know the level, like the level of each value can vary, and they ask find it recursively. So I I think your project resembles to that interview question that I had. I couldn't do it, by the way. But this, like, if you can do this project, then you could also solve that mid-level interview question. Figure of parcel and parsing. Lexical analysis. Parse tree. Yeah, yeah. This looks good, man. Researches to learn more. Actually, like, I really like this project, man. This is the level of, this is the correct level of applying DSA, actually. Because currently I am building like a blog website, e-commerce website, and I'm using Spring Boot framework there. And like, I feel like all I need to know is like overall structure, obviously, but you know when to call that function, where to call that function, or having service classes, and like, where do you call your database functions. That's all. But like, this is learning a framework thing, and this is learning DSA fundamental thing, I guess. Thank you for sharing it, by the way. um I guess I'll have to take a break now, because I don't have any energy for understanding building and extracting phase. Actually, this should be easy because we are using this sift down method. And actually, we use the sift down method in phase 1 and phase 2. Hmm. So actually, we completed the core part. So understanding this phase and phase 2 should be easier. Understanding this phase 1 and phase 2 should be easier because I think we completed the core part. So can you guide me a little bit? So, like, because understanding the start point of index like a I, and like we are going inverse, I mean, we are starting high and going to low. And why is that, by the way? And are we building max heap or min heap? But you say max heap. So like, I need to actually visualize this. So maybe we should create an animation for that. And we have extract here, and again, it's start from high and to going to low. So maybe we can uh, create an animation for these parts. If you say so, I will open my Blender. I do think compilers and interpreters is applied DSA because you are translating one language to another. You need to know DSA concepts. Maybe in one of them, like, I know, I know that in different languages, as you say, the sorting algorithms that they use may vary. Okay, I'm going back to studying my stuff. All right. Thank you for stopping by. I will try to create an animation for that, and I will take a break. Take care. Let's open this and start the MCP server and create that animation, because like, I don't I don't have anything for, like, I don't understand anything from this part. All right. You'll have invented bottom up yourself. Two quick supporting facts so you are not guessing. The last non-leaf. Oh. Hmm. The parent of the very last element. Leaves have no children, already trivial heaps. No pointing shifting them. So you start at the deepest parent and walk up to the root. Alright, alright, alright. I guess like those numbers and those formulations have meaning, obviously. So the Blender MCP is connected. Now I need you to create a blend file here in heap sort folder, and start building. And actually check the merge sort and apply the same structure there, because it has renders and nodes and preview frames and Blender folder, so that they are organized. So for our new animation, make it organized, all right? And don't dump all the code, or don't try to complete all the animation. Go step by step. Prompt me to verify the look of it, all right? Go step by step. So now we are creating the animation. Interesting. I guess I can run the start command project which. Let me run this command, because I guess there is no background sound. I guess now you hear the sound, guys. All right, all right. Let me open. Now it will build us an animation. Hopefully we'll understand um, the part, like oh my god, it got frozen again. So there is something wrong with this app. Open it again. This is the top of my notes. Let's go down, let's scroll down a bit. So the part was like a 3 phases, all right? I want to copy these and paste it down over here. So I guess we completed the shift down part. Let me type take care. All right. And we completed shift down, which is core part. Now it is time for understanding the building and extraction part by building the animation. Blender on a fresh default scene. Perfect. Here's my before I start design the teaching side, the teaching idea. Show the array as a binary tree. Yes, because the whole of heaps is the array is the tree. Yes, we know that already. We already know that. Before I animate anything, verify the look. Layout. Tree readable, spacing okay, or actually tell me what to adjust, or say looks good, and I'll move to step 2 animate build phase. Highlighting. What should we do, guys? Which part should we animate? Actually, first, as you say, first we should design, like decide which parts are we gonna animate, because the part I wanna understand is building and extraction phase. But um, like can we do it? Like can we create an animation for building and extraction part only? How would you design it? Because in another animation we can go deep about the sift down part, and also um, you can use the tree version, not an array version. What do you say? I need to build an animation for this. Let me check the stream. If the sound is all right. I guess it is all right, but let me check. I guess it is all right. I guess it is all right. Yeah. That's fine. Um, Good call. Let's lock the scope and storyboard before animating a single frame. This animation build extract only, yes. Sift down is a black box here, yes. When a node needs to sync, it just glides down smoothly to its resting spot, yes, spot. No comparison callouts, no is it large, yes, no, yes. Visual, tree-centric, wow, that's a good word. Drop the index array. You're right, go tree. I would replace the bottom index array with one small thing that only appears in the extract phase. Here's the storyboard. Phase A. Let me look at YouTube side too, if we have. All right. Phase A. Build. Caption amplify each parent bottom up. A glow pointer marks the current node. Walking bottom up. Each one black box sings. Drop the array. Fill ascending left to right. Animate the build phase. Two decisions for you before I build. Drop the index flood array entirely and use the only appearing sorting tray. My recommendation keeps it tree focused. Yes. Sorted order. Fill the tray so the final read ascending, or you prefer the max landing only. I don't know. Let's continue with this one. We need to build that animation. Heap sort build phase. We have our heap here. It is not valid, so we need to swap this. Actually, like this is not valid too. I guess we need to build it now. Let's see how is it gonna build. Let me drink my water. What time is it, by the way? It is 20 past 3. Now we are creating animation for heap sort. Actually, let me type it down. Creating an animation for heap sort in Blender. Yes, because I didn't understand the part for building an extraction. Like it said that um, like there were two for loops, I guess, and they start from leaf nodes. I don't know, something like that, and they start from high, as I call it, to low. I mean by decreasing, and I want to understand this building and extraction phase right now by building an animation for that, because I completed the part shift down. I mean, let me correct it too. I mean shift. Maybe we should remove this part as well. Shift down. We completed this part. Locked, dropping to array, ascending tray, tree centric, rebuilding the scene with movable value tokens. So a swap reads as two numbers gliding past each other and animating the build phase, color identity. Each value keeps its color, so you can watch the warm high values rise up to the top. Let's see. Let's see what will it do. How is it gonna build the animation? I tried it before and it performs very well, like a leetcode performs very well building animations, because we are using MCP, like a Blender MCP, and like it is recently announced actually, and it works really well even with the algorithms, because algorithms is hard. Action API animation built and saved. Let me render keyframes across the build to verify the progression. Like, do we have, like, is it really that fast? It says 205 keyframes. Like, let's see. Oh, it really finished. Let's see. Let's see how well it performed. I mean, all right. I don't know why we started here, actually. But at least I know that we picked the largest one among the children for the root. That is not valid heap. But why not start from here but here? So we swap. Yes. And then we go to the left child of the main root. And again, like it is valid, so we don't do swapping. Yes. Now we are back again to our main root. And since it is not valid, like the root is bigger, like not bigger than its children, so we pick the larger child. So we swap. Yeah. Oh, we do swapping again. Wow. Like this movement is great actually. This movement is great, but why did we start from here? I didn't understand that part, to be honest. But we have something here too. Like it is two, like seeing two swaps down, 8 rises, it says, but it should move like a whole animation a little bit up. But that's all right. Let's see. Build phase is animating correctly. Here's the progression across 210 frames. It was 200 anyway 5 at last time I checked, but no, yeah. Frame 35, yellow ring on. Why I don't see any ring, by the way? Is it because? Yes, this is much better. All right, this is much better. But like, all right. Two saying to leave. Yes, yes, yes. Root is now 9. Max heap build. All right. So now we are building our heap, basically. We are building our heap. The three design ideas all red, I think. Bottom up rising, black box things, color identity. Notice note note 1, it says. Which one is that? It is the child of main root. All right. Correctly does nothing. It was already the biggest. Yes, yes. There's already heap case you drive. Yes. Verify the build phase for me. The choreography read clearly. Pace okay. Anything to tweak before I move on? Say good to extract. Actually, the main goal here was understanding the build, but I don't understand the build. So the main goal for build phase is actually understanding the for loops start and end points, like this formulation. But I don't understand it by looking at this, because I don't understand why we started from like a 2, like a right child of 3, all right, and we check its heap properties, we check its heap properties, and we do swapping, and then we go to 9, which is left child of 3. It provides the it is valid heap. So like I don't understand this, all right. And also at the bottom of our tree we have like some sort of label, but it is not visible, like it is below the z index, all right. So, and also like the child, like a children of 9 and 8 is I mean not 9 and 8, but 9 and 2 is below the 0. So maybe you should move them. Actually we don't need to move them above, like up, right? If we can position our camera well, then we can see it. But currently I don't know. Currently, oh, like all right, now I am in camera mode and I see them amazingly. But the thing is, maybe you should show me the input array we have. Like I don't understand what we are building, like what we have, like I need to see input and output wise, all right, what we had and what we are building and what we get at the end of the operation, like this for loop, all right. And maybe you can add the for loop here as well, like a like the build for loop, all right. Only that part. Maybe we can create different animations, but in this animation let's focus on like a building phase only. Let's see. Let it transcribe my voice. Did I start? Oh, all right, that's fine. It's been almost 4 hours, guys, and like I want to take a break, but first I want to I want to understand this build part and then the extraction part. All right, because like we completed the hard part. All right, like only remaining thing is understanding the easier parts. So like for those parts, I need to understand the start and end point of those four of for loops variables. Condition start. So if you guys have any question about what I do, we can talk about, we can chat about it. Let me. All right. Interesting. Now I'm waiting for Cloud to build that animation. Actually, while it builds, we can create another session, AI session, and ask it to, can you give me the code for heap sort algorithm? Actually, like the sift down phase, like we created our own sift down phase. So that's the most important, feedback. Yes. Why the loop starts? Yes, this is important. Like n divided by 2 minus 1, like why? I guess it has something to do with the starting from leaf or something. Two facts about heap as an array of size 7. Where do leaves live? Like at the end, right? I get, yes. This has to do something with the fact that we don't need to process the leaf nodes, and like imagine we have this array and like a first node, second node. All right, it continues like that, and at certain point the remaining nodes are always like a leaf node, like a leaf, right? Leaf, like imagine a tree, and for these nodes we don't need to process them and verify them if they are heap or not, because they don't have any children. So our code, like our only goal for heap was the parent should bigger or equal than its children. So this is the only rule we have. All right, so like we don't care about the leaf part, and leaf part is like a certain, and the exact index is n divided by 2 minus 1. So I guess like this index is n divided by 2 minus 1 minus 1, or I don't know, I'm not sure about this, but most probably correct. So like we only care about, like I would say we only care about this part, but we start from the end. So maybe I should ask why we start from this to 0. Actually, yes. So we start from here, basically. All right, we start from here and we go to there. So basically, I guess we start from here, like a right child, and then we go to that way. I guess that is correct. Two facts about, yes. It is about the leaf nodes, all right, and the fact that we we shouldn't process them. A node I has a child only if 2 times I plus 1 equal like a smaller or equal than n minus 1. A node I has a child only if I like I. All right, flip that. Node I is a leaf when it is bigger. All right, if it's bigger than half of the n. All right, so starting from 3, they are leaves. All right, this is the formulation we have. So the last non-leaf, like the term, like the term is this. All right, like this is the thing that I wanted to understand. Last non-leafed node. That's why the loop starts at 2. There is simply nothing to do above it. But another important thing is, why do we start from there and go to the 0? Why not start from 0 to and go to the that thing? Why can't all right? Why can't now? Like, all right, like without asking, it answered, I guess, or I included in the previous question. Because shift down trusts that the subtrees below are already heaps. If you start low and walk up to the root, then every time you all right. I started not understanding it, so I will end here, guys. I will hand the stream here. So thank you for dropping by and joining me. In this session, we studied bubble sort and heap sort. And for heap sort, we completed the core part. All right. And in the next LeetCode session, we'll continue from here. And I should save its ID. We are going to continue from here, like from this session. Actually, it was, oh, wonderful. It was building the animation as well. Look at it. It looks wonderful. It looks amazing. So I think I need to save these two. No, like which one we were using for building the animation. All right, I will check it out and save the IDs of them. I guess, let me check. Let me check its name actually. Come on. Yes, this is like, all right, this should be it. But I guess after building part of the Blender animation, I started asking some other questions, right? No, yeah. I don't know. I'm getting tired, guys. So like, and in the next stream, I will be studying some Python. So thank you for joining me, and take care.